Welcome to the Explainer. I am so excited to jump into this one because we're looking at a piece of everyday magic. Seriously, you probably poke, tap, and swipe at this technology hundreds of times a day without even thinking about it. Yeah, we're talking about touchscreens. Think about it for a second. How does a solid, unmoving piece of glass know exactly where your finger is? It honestly feels like magic, right? But it's actually just a brilliant feat of modern engineering. And in this explainer, we're going to solve this daily mystery that we all just kind of take for granted. So here's our game plan. We'll start with the fundamental magic of touch, pit physical pressure against electricity, and then dive right inside a modern smartphone screen. From there, we'll see how engineers solve something called the ghost problem, and finally wrap up with why this all actually matters in your day-to-day life. All right, let's kick things off with part one, the magic of touch. Now, despite all the endless types of screens out there, from your iPad to that self-checkout kiosk at the grocery store, the actual fundamental interaction really boils down to just one of two physical triggers. It's either the mechanical force of a physical push, or it's the natural electrical disruption caused by the human body. Which brings us to our two heavyweight contenders, pressure versus electricity. Let's do a quick head-to-head. First up, we've got resistive touchscreens. You can think of this technology almost like a microscopic mechanical switch. It basically happens in 4 quick steps. First, you physically press on the screen. Second, that pressure makes a flexible top layer, usually some kind of polyester, bend inwards across a tiny, tiny air gap. Third, that top layer physically touches a bottom layer, and since both of those layers are coated in conductive material, boom, they complete an electrical circuit. Finally, the device measures that current flow to calculate the exact X and Y coordinates of your tap. It's simple, it's incredibly reliable, and it's totally pressure-driven. But then we have the capacitive model. And this one is entirely different. A capacitive touchscreen detects input through the electrical properties of the human body itself. It literally doesn't require pressure, just a super light touch. It's actively sensing your conductivity. When your finger gets close to the screen, it disrupts this constant electrostatic field. Basically, your finger's actually kind of stealing a tiny bit of electrical charge from the screen's field, and the sensors pinpoint exactly where that little theft occurred. And these physical traits totally dictate how the screen feels to use. Because the resistive screen relies on physical pressure, it works perfectly fine if you're wearing, say, thick work gloves, or using a plastic stylus, or even the back of a pen. But it is generally limited to just a single touch. Capacitive screens, though, they rely on human conductivity, so they just need a gentle, fluid glide of a bare finger. And crucially, they are highly capable of multi-touch gestures, pinching, zooming, all that good stuff. Because of these huge differences, you find these screens in completely different environments. Resistive screens need a firm job, and they work with literally any object, so they are the undisputed champions of harsh, outdoor industrial settings. Think of rugged outdoor ATMs or factory control panels. Capacitive screens don't have that squishy, flexible top layer, so they offer incredible optical clarity and multi-touch. That makes them the absolute gold standard for clean, indoor consumer electronics like sleek smartphones and medical tablets. Okay, so let's zoom in on that consumer side for Section 3, inside the smartphone screen. The device you're probably holding right now uses what's called PCAP, or Projected Capacitive Touchscreen Technology. While those older resistive screens used to be everywhere, PCAP is the breakthrough tech that Steve Jobs famously popularized with the original iPhone back in 2007. It changed everything. It overcame all the old limitations by offering this incredible sensitivity, a smooth hard glass interface, and the ability to instantly recognize complex multi-touch gestures. But how does it actually track your finger through solid glass? Well, the secret sauce is a material called indium tin oxide, or ITO. It's a highly transparent conductive coating. Manufacturers use this ITO to literally print invisible rows and columns of electrodes directly onto the sensor glass beneath the surface. It creates this microscopic grid, and the denser the grid, the higher the touch resolution. All of this is sandwiched right below your consumer cover glass, which, by the way, is usually only about 0.7 to 1.1 millimeters thick, super thin. But here's the thing, a grid is completely useless without a brain. The second a touch is detected, an incredibly powerful controller chip has to process those raw analog signals, those tiny, tiny changes in capacitance we talked about, filter out all the background electrical noise, and convert it into digital coordinates for your operating system to understand. And amazingly, in some heavy-duty industrial setups, this chip has to drive those signals through protective glass up to 8 millimeters thick.
It requires some seriously sophisticated signal processing. Now, let's dive into part 4, solving the ghost problem, because making multi-touch work flawlessly was actually a huge engineering hurdle.
See, early on, a lot of capacitive screens used a method called self-capacitance scanning. This system measures the capacitance of individual electrodes relative to the ground. Basically, it scans the rows and the columns one at a time. So if your screen has 10 rows and 15 columns, the system only needs to perform 25 total scans to check the whole screen. 10 plus 15, right? This makes it insanely fast, but it comes with a massive blind spot when you try to use more than one finger. That blind spot creates a major error known as ghosting. It's honestly this fascinating technical mystery where the system essentially hallucinates touches that aren't there. Imagine you place 2 fingers diagonally on the screen, let's say on coordinate x2, y2, and coordinate x5, y4. Because the system is only scanning individual rows and columns, it just registers activity on rows 2 and 4 and columns 2 and 5. The controller gets completely confused and actually generates false ghost coordinates at the mirrored points, x2, y4, and x5, y2. It literally has no way to know which diagonal pair is real. It totally ruins the multi-touch experience. So how did they fix it? The really elegant solution to the ghost problem is mutual capacitance scanning. Instead of scanning those lines individually, this newer tech scans the actual intersections of the rows and columns. It creates a tiny little capacitor at every single overlap. So back to our example, a grid with 10 rows and 15 columns now requires scanning 10 times 15 or 150 total intersections. Now, when your finger touches the screen, it takes a little charge away from the localized field at that specific, unique intersection. To summarize this massive technological leap, self-capacitance is super fast and requires way fewer scans, but it completely falls apart and suffers from ghost points if you use multiple fingers. Mutual capacitance, on the other hand, requires a ton more processing power from the controller chip to scan every single intersection, but the payoff? Flawless multi-touch tracking. You can literally put all 10 fingers on a mutual capacitance screen, and it will track every single one without a single ghost. That's why it is the absolute standard for modern devices today.
Which brings us to our final section, why this actually matters in your real life.
Well, understanding all of this is exactly why you experience that universal freezing cold struggle of trying to send a text message with thick winter gloves on. Your smartphone is a capacitive screen. It needs the electrical conductivity of your bare skin. The thick glove just acts as an insulator, completely blocking the electric field. But when you walk up to an outdoor ATM in those exact same thick gloves, you can tap away without an issue. Why? Because that ATM is a resistive screen. It only cares about the physical pressure you're applying. It perfectly highlights the distinct limitations and strengths of each technology. And the tech isn't standing still. The future of touchscreens is actively solving these exact limitations. We're already seeing high-end controller chips using advanced algorithms for water rejection and glove detection on capacitive screens. We're seeing hybrid panels that actually combine the ruggedness of a resistive screen with the fluid multi-touch of a capacitive one. And incredibly, engineers are now looking to replace that brittle ITO grid we talked about entirely with transparent, flexible films made of silver nanowires or even graphene. Which leaves us with this provocative thought to close out our explainer today. As we move away from these rigid glass grids, will emerging conductive films like graphene eventually make our touchscreens as flexible, thin, and durable as a piece of paper? I mean, the invisible grid in your pocket is already a marvel of modern engineering, but it looks like its evolution is really only just beginning. Thank you so much for hanging out with me today. I hope you walk away with a whole new appreciation for the absolute magic hiding right beneath your fingertips.